So the reality gap as a problem has existed since early simulator days in the late 80s, early 90s. Since then, we have seen a myriad of approaches from evolutionary algorithms that adapted the simulator to real trajectories via systems that learn an explicit model of the discrepancies between sim and real to data-driven approaches such as domain randomization. Now it's 2022, and we are left to wonder if we haven't solved the issue yet. On one hand, we have new simulators, better physics, new Sim2Real methods with better sample efficiency. But on the other hand, we have contact-based robot tests that are hard to model correctly and on model effects that might mess up a sim train policy. So we are very excited to hear the opinion of four experts in robotics, and if we can all hang up our hats and call it a day or not. So this debate will be structured as follows. We will start by introducing our four panelists, two arguing for and two against the proposition. Note that we ask our speakers to take a particular opinion in the debate, which may or may not reflect their personal opinion. Each speaker will then have 5 minutes to deliver their opening statement. We will then transition to the actual discussion for about 30 minutes, and then wrap up the debate approximately 5 to 10 minutes before the end to allow each debater from both sides to deliver their closing argument. The moderators will try to stay out of the debate, but might interrupt in order to make sure that we cover as many interesting questions as possible. So with that, I will hand it to my colleague Florian for the introduction.
Mute myself. Okay. Thank you, Melissa. I'd like now to introduce the speakers. We have on the side that is in favor Animesh Garg. Animesh is an assistant professor of computer science at University of Toronto and a faculty member of the Vector Institute. His works span a variety of robots and simulators, but you might know him for being the first scientist to put a robot dog on a skateboard, or for thinking it's a great idea to give a robot a knife, but only if you can simulate it first. Next up in favor, we have Fabio Ramos. Fabio is a principal research scientist at Nvidia and professor in machine learning and robotics at the School of Computer Science, University of Sydney. He's a man of mystery because according to Archive and Google Scholar, he has a paper on real-time tracking with almost 1,700 citations, but mysteriously, you can't find it on his website. He also spent a lot of time in the past with Gaussian processes and seems to be very interested in differentiable simulation lately. Then against the statement, we have here Dorsa Sadigh. Dorsa is an assistant professor in the computer science department at Stanford University. With autonomous vehicles and armed robots, she's working on making them safer and more reliable, especially in the vicinity of humans. To this end, in a lot of her works, you'll see her grad students stand inside the danger zone of the robot arm. And lastly, against, we have David Su. David is a provost chair, a professor in the Department of Computer Science, National University of Singapore, and the director of Smart Systems Institute. He's famous for motion and general path planning. What started out as 2D particles in a box having to go from one end to the other via tight passages is now a Boston Dynamics spot dog with 3 head-mounted forward-facing cameras having to navigate around campus and through office corridors. Please give a hand to our debaters. So now we'll start with the opening arguments. And the order is going to be first Dorsa arguing against, then Animesh in favor, David against, and lastly Fabio in favor. And after that, like Melissa said, we'll go to the freeform argument. Also, for the people standing in the back, there are still seats all around. Please knock yourselves out. So Dorsa, please take it away.
All right. This is on, right?
Yeah.
It's on. Okay. Do I just like win by being in person here?
Yes.
I think, yeah David and I just win because, like, you know. Yeah. So, okay. So I'm going against the argument that Sim2Real is not solved. I think all of you agree that Sim2Real is not solved because otherwise, why were we here and why would we have this workshop if it was solved? But specifically, I want to talk about a few different directions that I think Sim2Real is not solved. So I have 5 different reasons. So the first reason falls into the category of having realistic simulators. So the type of systems that we want to build are not solid rigid objects, like dealing with solid rigid objects most of the time. For example, if we need to deal with deformable objects, we don't have good simulators for that. In general, in the space of human-robot interaction, one of the projects that we are looking at is how can we help people assistively feed themselves. And in this project, I don't work on simulators. In this project, we decided to like pick a simulator, the best simulator that is out there, that can simulate food and can simulate picking up food, skewering food, and then transferring the food to a person's mouth. None of that really exists today. Like it's actually kind of sad that we don't have good simulators of food or a person's mouth or any of these deformable objects, or how they get deformed, right? Like how do they get cut? How can we skewer food? And these are the type of tasks that we are actually like really like they're safety critical tasks. These are tasks that I really care about, and I don't want to test on my graduate students when we are thinking about assistively feeding someone, picking up food and bringing it to a person's mouth. But unfortunately, we ended up testing this with graduate students because we really like don't have good simulators that are anywhere like close to reality, and that was just not possible. So my first argument is we're far from reality when it comes to dealing with things that we care about, deformable objects, like in general, like complex interactions that we care about. The second type of thing that we care about in general when we have robots is dealing with humans. So in general, I'm pretty interested in human-robot interaction. If I want to do anything that models humans, we don't have good simulators for that. Purely modeling human behavior, I think we are getting closer to that, at least for navigation type tasks. For example, we might have data sets of cars driving, and based on those data sets of cars driving, then I can have some idea of how humans drive, like around other humans. But like when it comes to more complex manipulation tasks, again, I don't have good models of how humans act in the environment. And that's just purely acting, not even interacting. But also like one might want to care about how humans actually interact in the presence of a robot. And that we don't have any of that. So in general, I think dealing with humans is pretty complex. We don't really like have good models of humans in a simulator or how a human can actually interact with other agents. Again, there's a little bit of preliminary work around modeling humans within simulators, but very far from reality. One example of that is just the fact that human data is pretty different from simulated data. We have a recent work where we are looking at learning from play, and we tested this on simulated data. Everything was great. The moment we tried to transfer that with real human data, everything failed. Like nothing was working. And part of the reason is like even for simplest tasks like pushing an object, there's a lot more variability in human data, and that is just not present in our simulators today. So we need to think about what type of data we are simulating, and I think that is one of the other key questions that we don't have a good answer for. Moving along, like what are some of the other reasons we don't have the Sim2Real solved is just developing realistic scenarios. Again, going back to the space of autonomous driving, right? Like we really care about having near accident scenarios and near the end of the risk spectrum scenarios. And we don't really know how to like maybe we have a good driving simulator, but that doesn't mean that we can generate these realistic scenarios, right? If you want to try to generate a near accident scenario, the best you can do today is your car like running into the wall, and that's not very realistic. So we don't really know what to simulate like in a lot of settings too. And I think that is also part of the problem. Moving along, I think the fidelity of the simulators is also a question. Like, what is the fidelity that we want to like stay in? What is the fidelity that we want to live in order to talk about safety or generating scenarios or doing tasks? So that is also a big question. Do we want a high resolution or low resolution, depending on the type of tasks that we want to do? And that is also not clear. And that is very much tied to how fast we can simulate things. So in general, like there's a lot of excitement around differentiable simulators, and in general using simulators for tool design, for control, but a lot of these types of systems are extremely slow. We recently decided to use a differentiable simulator for tool design, and it's just like incredibly slow to do anything like using the simulator. Part of the reason is that usually the reward functions, cost functions we're optimizing are extremely non-convex, and just navigating around like those cost functions is even if you have a differentiable simulator ends up being pretty difficult. So just to summarize, so the things that I covered is I feel like we are far from reality when it comes to like objects, like deformable objects, like complex objects. We don't know how to model humans, human behaviors, human interactions, irregularities that's present in human data. We don't know what it is that you want to simulate a lot of times, like generating realistic near accident scenarios. And then there are questions around like computation and fidelity of simulators. Like a lot of times it's pretty slow to use these types of simulators. So with that, I'm going to switch to Animesh.
Thank you, Dorsa. I think this was a wonderful set of arguments. Pretty hard to argue against, actually. Nonetheless, I've been given the baton to defend simulation. So let me start with instead of talking about simulation, let's talk about two particular problems. These particular problems are near to me because this is how I started my PhD. 10 years ago, when folks were starting out working in grasping, and not even multi-finger grasping, just plain old two-finger grasping or parallel jaw grasping. And then the other problem is dynamic walking. 10 years ago, both of these problems were considered by experts, not by me, but by experts, real ones, that they are both contact rich and simulators are just never going to get around. About 10 years ago, we did not have a lot of simulators and they were all very hard to actually use. Cut to today, one could argue that both of these problems are now actually solved with simulation, right? So primarily, these systems are trained with simulation. In a lot of these cases, both physics and sensor simulation, if you will. Sensors can involve a variety of things, whether they are force or, let's say, visual or perceptual sensing. So what has changed? One could argue the technology has evolved to a point where these problems are actually or can be considered close to solved. One, we have better simulators, and the underlying better physics models or better constitutive models have come a long way in the last, let's say, decade or two, which does involve both rigid contacts, but also soft objects and maybe even, let's say, cutting. One could even argue an example of that is a lot of these problems that we find interesting are not necessarily research problems in, let's say, computer graphics. According to them, a lot of these problems are actually solved. Secondly, the speed of these simulators has actually come a long way along with equipment and hardware. And finally, the ease of use. We as roboticists can use these complex physics simulators, which is completely in antithesis to Dorsa's experience, it appears, is the ease of use. In many cases, we do not need to be PhD in physics or graphics for using these simulators. A lot of the examples in reinforcement learning or even new control community could point to directly using a bunch of these frameworks. And finally, ideas like differentiability do help in essentially making solution finding easier. So differentiability is not necessarily required for simulation itself, but finding solutions for these sort of control problems is easier. So what does this entail? What it entails is basically downstream use cases, allows us procedural environment generation. Yet again, the procedural environment generation can be done through pure random choice of parameters, which we know and love by dynamics randomization. But I think it's not just dynamics randomization. You can also do adversarial choice of parameters. You can also do curriculum design in these cases. And many of these things exist in literature where people have shown that these kind of designs do help a lot. And finally, even if there are problems, there's a lot of recent work which says we can do online system ID through interaction. This system ID, of course, is a concept from controls, but this sort of digital twinning, if you will, can be done not just for physics parameters, but also can be done for geometry, shape, scene as well. And this, in effect, has allowed online construction of environments, and fast simulation allows you to adapt policies on the fly. And without naming names of particular recent papers, I would argue a lot of the recent interesting robot learning research or even skills, I'm much more familiar in robot manipulation space, would not exist without the simulator in the loop. I would rest my case and move over to David.
All right. First of all, let me thank the organizers for handing to me, Dorsa and me, the easier side of the argument. I think I will first start by give a particular characterization of Sim2Real problems. To me, the simulator is simply a model of reality. Right. So from this perspective, I think I will summarize what Dorsa and Animesh said as two sides of increasing the fidelity and the accuracy and the in general, the capability of the simulator. By closing the gap between the sim and the real, presumably the task of Sim2Real transfer will become easier. And I agree with that. There's no doubt about it. But I would building on top of that, the problem of Sim2Real is not just that equivalent to improving the fidelity of the simulator. The problem of the Sim2Real includes that of building better simulator, using the simulator for reasoning, for learning, and finally, that takes the solution that we got out of the simulator and transfer it to the real. And when doing that, we must close the Sim2Real gap. Right. So from this perspective, the problem of Sim2Real transfer is almost equivalent to that of robotics. Right. So we believe that a robot, an intelligent robot, is a reasoning agent, and we need some kind of model for the robot to reason. And once the robot develops a solution in its mind, and that solution has to be executed in the real world, and hopefully that actually works. If it doesn't, we get feedback signal from the real world and try to improve the solution. And the robot has to iterate on this process. This is exactly the loop of closed loop robotics and perception and action, right? So now, even if we have a high fidelity simulator, the question I want to pose over here is, do we actually want to use it? Is there a reason for not using it? Well, there are two reasons I will put over here for not using it. One, as the fidelity of a simulator increases, the computational cost of reasoning over these models also increases. So I may prefer a model that is simpler so that I can develop the first cut approximate solution faster. And that solution may actually be good enough in the sense that all models are wrong, some are better than others. If the solution that developed out of the simpler model would actually be able to transfer, and I would rather prefer a simpler model. Simple models usually is also more robust, right? Now, regarding the transfer, now the problem of in order for a solution to transfer from the source domain, in this case, the simulation, to the target domain, which is the real, I believe that we would have to have some understanding of the structure of the gap between the two domains. And well, I think that sometimes it is indeed true that, for example, in the domain randomization approach, that we could sometimes it is possible that we could use sufficient data to cover all the entire policy space, and during the Sim2Real transfer, we just pick from the collection that are pre-computed and use the one that is the most suitable. But not all problems like that, and the hardest kind of robotics problem is often not like that. And now in those cases, it is essential we understand that the part of the structure of the policy space that needs to be transferred and take advantage of the structure in order to facilitate both efficient and robust transfer. That's all from me, and pass on to Fabio.
All right. Thank you, the organizers, for organizing again this super useful workshop. I think we love the vibe and the ideas discussed in this workshop. Thanks, Florian, for reminding me that I need to update my website. So, well, I would start, just as David did, with a formal definition of Sim2Real, or the Sim2Real problem. I think the first thing we need to agree on is what Sim2Real is. And to me, Sim2Real is the problem in which a given method, and that method could be for perception or control, is first developed, and if it involves machine learning, is training simulation, and once deployed in the real world, achieves comparable performance. Okay, so that's the definition of the Sim2Real I usually use. And I would argue that that definition is a little bit blurry depending on which field you go to. But with this definition in mind, I also want to phrase again the motion here, the statement we are debating, and the statement says, at this point we have practically solved the Sim2Real problem. I think the word practically here is quite important. Practically, I would argue, means nearly, or in other words, for many practical purposes. And that's the sentence I'm going to be debating on. As for the first part of the motion, at this point, I would say that, David mentioned, and Animesh as well, that simulators have improved in terms of their accuracy, but which I agree on. But I would say that even more than the accuracy, the major developments in simulation technology recently, at least, have come from speed, from the ability to simulate processes faster, and in many cases, in parallel. So we can do vastly parallel simulation for many problems, not all, but for many problems. And once you consider that we can do very parallel simulation, you can use techniques such as domain randomization, which obviously has different names in other communities. But the idea is, if I'm simulating not one reality, but many realities all together, I can, in this set, incorporate the complexities of the reality, even if my simulator is not perfect. But in the composite, all of them together, I capture the reality relatively well. So that's my argument number one. So first of all, we are not talking about just a single simulator, but today, as computational grows, we can deal with many real problems. The second point I want to make is that even if you believe, even if you think that the Sim2Real problem is not solved, you have no other way but to act as if it is solved. And the reason for that is, as we evolve the community, we evolve the robotics community to more and more complex tasks, the ability to deal with problems in very complicated scenarios and collecting real data for that is almost impossible. So you have very few tools at our disposal, and perhaps the most important one are the simulations. So you need to believe that Sim2Real is solved for your practical purpose. If you want to make, if you want to evolve in your own research. My final argument is that, well, the Sim2Real problem is one part of the real to sim to real to sim, and so on, a loop, as David mentioned. If we can go back to reality from time to time, doesn't actually need to be many times. From time to time, we collect one or two real trajectories and sensory data and feed that back to our simulation. We can much better design a cluster of simulations, right? A group of simulations that in expectation recovers the reality as close as possible. And once you have that property of recovering reality in expectation as close as possible, I will declare that the Sim2Real problem is solved for practical purposes. So that's my remarks, initial remarks, and I move on to the organizers, I guess.
Okay. Yes. Thank you, everyone, for your opening arguments. And now, please address each other's remarks.
Should I go first? I don't know. Is there an order or
There's no
order?
order.
Okay. We can, Okay, so I want to kind of like push back on one of the points that was brought up by both Animesh and Fabio. So Fabio was like, if we have like simulators are important, and there are many different realities that we can have in a simulator, and because we have these many different realities, well, that helps us to build better, more robust systems. And I think Animesh was referring to like a lot of tasks are solved like using simulators. So the reason I want to push back on this is sometimes like we get a false impression that the task is solved and it's actually not solved. Again, going back to this idea of learning, let's say learning that we want to just push an object, right? So we can have a simulator for pushing an object. We can generate a lot of data in this simulator for various ways of pushing an object. If that data is not coming from a real human, it's really not going to capture all the things that we care about when we are thinking about pushing an object. What happens when a person comes in and provides data for pushing an object? It's going to be very limited to what it has seen in the simulator. And it gives us a false impression that we know exactly how an object is going to be pushed. And that false impression that the task is solved. But again, we haven't learned many different other ways of that is just not present in our simulator. So the task is solved to the extent that our simulator is able to capture like a knowledge of reality. Like if we are good at like capturing reality, then we can simulate many different realities. But in practice, we might miss a lot of things. And I do agree with Fabio about and everyone and David, and I think everyone agrees with the real to sim to real to sim kind of like loop of things, and that can be one way of addressing that. But just like sim to real the way it is today, I feel like it can sometimes give this false impression that the task is solved.
Oh, yes. Sorry. Technical difficulties. Yes, Fabio, David, and Animesh, feel free to unmute yourself and respond as you see fit.
I can address some of the comments from Dorsa. Animesh, I guess we'll do one team, then the other team, see how it goes, right?
Yeah, let's try that.
I want to bring one example that actually doesn't come from our community, right? I mean, this idea Sim2Real is a term we use here in our community, but the problem is actually much broader than what happens in robotics. You know, let's think about aeronautics, right? And the design of airplanes. For example, we still don't know exactly what happens very close to the wing surface when you see the interaction of fluid dynamics with the harsh, you know, the hard surface in there and the friction of fluids with that. We still struggle to model that thing properly. However, we still fly airplanes, don't we? We still believe simulators are useful, and a lot of the computation that goes in the simulator actually helps to reduce the cost of designing the entire system. So from that industry point of view, simulators are a critical part of the problem. And for any airplane design, we rely a lot on simulation. And I think that idea can be translated to robotics, right? So for example, the formables. Yeah, the formables might be difficult to do. You don't want to run, you know, finite element method for every little thing. But I actually find very interesting to see new developments in which the finite element is replaced by other faster, less accurate models. And we can run many of those in parallel. Again, with the idea that in expectation, we recover reality. I will talk about the humans, you know, next time I have a chance to speak. But yeah, I'll let the others comment now.
All right, let me take up Fabio's point. I think Fabio, in his very careful redefinition of our debate statement, I think he tries to convince you that robotics is mostly just about predictability. If I have, right, that's what a simulator does for us, right? Predict the future in n time steps, what state of the world is going to be. If we have a high fidelity simulator, if we have a high fidelity simulator that is fast enough, then the problem of robotics becomes much easier than it is, right? I don't deny the fact that sometimes it becomes easier, but my main point is that I want to say categorically, robotics is not the problem, is not just the problem of predictability. Robotics is a problem of making the right decisions. Right, so this is, I think, now we can achieve good decision by having a good predictive model, but we don't have to do that, right? So let me say what I mean by doing that. All right. So to me, a good simulation model to an autonomous, a modern autonomous system is somewhat similar to Newton's law to analytic methods of calculation, right? So let's just think about what happens before the time of Newton. And we want to figure out how to throw stones and things like that. We don't know how. I mean, we don't know how to throw in such a way that it will hit the target reliably. And then Newton tells us about Newton's law, these trajectories and stuff. We do some calculation and tilt the gun barrel to a particular angle, and we can hit the target much better than before, just by paper and pencil and do some calculation. Once we have this powerful Newton's law as our predictive model, I can do my analytical calculation much better. Right now, if we coming back today, now if you give me a better simulation model that's in the sense of faster, more accurate, I could use it in the same way that the analytical method can take advantage of Newton's law and so on and so forth. We could do the same thing, but at the same time, we must keep in mind that as we increasing the accuracy of the model, the computational cost also gets higher and higher. And I really love the example that Fabio just gave about aircraft, simulating airflows around the aircraft, right? So in the early days of simulation, all we can get is some kind of this very much simplified finite elements, like of a kind of a shape of the leaf that put into the simulator, and we simulate airflow over there. And later on, as the computation method, as we get more powerful computation computers, we throw in the entire airplane into the CAD model of the airplane into the simulator, and then we can do much more accurate simulations. But the question is that at some point that will reach, for various reasons, that either because we reach the limit of our computational power, or we want to make real-time decisions that are just beyond our computational budget. And therefore, we must adopt models that are simpler than the highest fidelity simulation that would actually offers us. At that moment in time, the orthogonal to the issue of predictability, we have the issue of decision making. Right. So we want to use a simpler model to actually make the right decisions, just for the same reason that even though that Newton's law is actually wrong, right? And we could use quantum mechanical model to drive cars if we have really powerful computers, but we don't do that. We would rather use Newton's law to reason about motion trajectories and so on and so forth. And we reason about quantum mechanical effects only if we fly something really, really fast. Well, we probably haven't invented anything fly that fast yet, but that's my point.
That's very good. I'll have one argument each for both Dorsa and David. Let's start with an argument for David. So David argued that the models don't need to be correct for you to make reasonable decisions. Sometimes sufficient models would do. But that is exactly what folks in simulation are arguing, that simulation models are indeed sufficient as they stand. More practically, I think the way to think about simulation, which often the community thinks of as a single word, is more than just one word, right? Often we mix up things. I would argue, and this would probably respond to some of the concerns that Dorsa had. a simulator, at least the word as we are using, is a combination of, I would argue, the actual underlying physics engine, where you're basically stepping through time, assets in the sense where what models, shapes, behavior models, generators you're using, the sensor simulation schema, the rendering, if you will, and finally, user interfaces. A combination of all of these four constitutes what we call and use a simulator. Often, the question is, for example, Dorsa gave a very good example of food manipulation, right? Now, one could argue the question, is food manipulation in simulation not doable, or can we as robotics researchers not do it? At the same time, I do want to say this. Robotics researchers are particularly special because we are asking all of ourselves to learn everything from control perception to physics simulation, while other people in other domains only learn one of these things. So it can be actually very hard, right? So it's nothing to take away from robotics researchers as their sort of skill set. But more importantly, the question is, a lot of these things are indeed doable. If not, these would be active research problems. Often these things are basically in this weird space where one community thinks that these are a solved problem, but it's not yet directly useful. So a lot of this often falls into this idea of like the user interfaces don't exist. The physics exists, perhaps the sensor simulation does exist, but the user interfaces don't exist. Another option could be, again, as Dorsa mentioned, that the data for generating the right behavior models may not exist. I think here I would draw parallels with computer vision community, let's say 2014 to 2018. In that setup, often a common methodology of research was, if you can create a data set for your problem, then you can solve the problem. I would argue simulation is the data factory for robotics. You have to figure out what problem can you create a simulator for, and I think Fabio already mentioned this. If you can do that, then that problem is attemptable currently. The same was true in vision. There are many interesting problems, but if you don't have a data set for that problem, there's not a lot of progress you'll be able to make. And people spend lots of time thinking about how to create that data correctly. And I think a lot of our research could also focus on how we can use the current set of tools to create the data that we need. Sometimes it would be, of course, very easy to use, easy and right away. Sometimes it will require thinking about how to calibrate, use some real data, or perhaps use some human behavior data to get all of the data distributions correct.
Okay, so I like the way that, Animesh was kind of like looking at these different components that go into a simulator. And I agree that, like all of these different components exist, and we really need to like push on each of them depending on like what the problem is. So I agree with that. So I want to kind of like push back maybe on one point, which is kind of bridging like these categorizations that Animesh was just referring to. And the point that Fabio brought up earlier, which is if you're not like not everyone should be working on not that everyone should be working on Sim2Real, but Sim2Real is like the answer for like a lot of like our robotics problems. If you want to push on them, you should really be working on the Sim2Real aspect of it. And I don't necessarily agree with that, specifically for this categorization that Animesh mentioned, right? Like if we don't have the right data today, or if we don't have like the physics model today, again, going back to the food manipulation side of things, if I want to just do like byte acquisition for transferring food, I don't have good simulators for that today. Okay, it would be wonderful to have good simulators for it, but I don't think that is the thing that's going to answer the problem of assistive feeding today. Sure, we don't need to have like the most accurate representations of food. Maybe like having somewhat of a not as accurate representation would be sufficient. But even without that, like in reality, right, I could write down like even model-based like policies with parametric policies where I can just do a search of those parameters in real without the need of any simulator and try to like attempt that question. So it's not obvious to me that for all of our problems, we need to like go down the route of Sim2Real, specifically for byte acquisition. Like we had the option of going and making the simulators better versus just go in reality and try to like attempt the question in real. And it seemed like the second approach was more promising compared to like going and building the right simulator for food. I think it would be nice if someone does that, but like doesn't seem to be the right answer.
We're doing the opponent's case right now.
It's got melded. Well, I'm not really, right? Because I'm arguing that if I want to solve robotics, then I don't necessarily need to have this simulator because, well, we don't have the Sim2Real. I'm arguing Sim2Real is not solved for, let's say, byte acquisition. And it is not solved, and I don't think it is necessary for specifically byte acquisition or for some of the robotics tasks that we would want to achieve. It would be nice if it was there, right? Because then I could like look at all the other environments and all the other settings, but it doesn't seem to be the first step for me who really cares about byte acquisition.
Let me just add on to what Dorsa said, right? So first of all, for robotics, we don't necessarily have to solve the problem of simulation, high fidelity simulation. If we actually indeed have one, we may not have solved the problem anyway, because that I have to do reasoning over the, as I repeatedly said, that to me, the simulator is just a model. In order to have the policy and controller, I have to reason over the model. And that problem itself may be hard, right? If you think about the entire domain or the field of planning, it simply says that give me a model of the world, and I'll reason about it. And we know that planning is hard, and it's provably hard. Therefore, that the simulation alone is not a solve our problem of robotics, right?
Well, I will address this comment by saying that yes, a single simulator alone might not be sufficient, but thousands, each one slightly different than the other, and is in expectation, recovering reality, can be a powerful tool. One comment I want to make to David when he mentions that well, Sim2Real is not just about recreating or predicting reality. It is also about the decisions we make in that environment, which I could not agree more. Is part of the Sim2Real problem. Even in my definition, right, to say, well, I want to develop something that has similar performance in simulation and in real. If possible, I would like to bound how large the gap might be, even before attempting anything in reality. And that includes this defining policies. So a policy, so let's say a policy or a control method or an algorithm that is designed, trained, refined in simulation. And this simulation is not a single deterministic simulation that says, okay, if I roll out this strategy here, I will end it up in this location. But actually says, well, if I have 1,000 versions of this, and I can roll out all of these 1,000, I will end it up in this set. If that set matches the set that you expect in reality, and reality is non-deterministic. Dorsa gave excellent examples of realities that are non-deterministic. So, for example, modeling food, there's, eventually there are the chaotic components to that process, which will lead you to realities that have a set as a possible outcome. Humans in the loop are another examples, because humans act in many ways unpredictable ways. But if you look at patterns of hundreds, sometimes thousands of humans, you look at the working psychology, humans are modeled deterministic as stochastic behaviors, right? So you have distributions of human behaviors. And since we have distributions of simulators, we can recover these complexities in there, right? We can recover the complexities of simulation and the complexities of predicting the output, as the output will not be deterministic. So again, for any practical uses, that recovery of the expectation of realities is very much solved, in my opinion.
Right. I feel compelled to respond to Fabio now, right? Now, so I think that you actually very nicely defined the complexity of variability of the real world, basically as uncertainty and variability, right? So, and now we are going to reason under this variability and uncertainty and come up with controllers and policies that operate reliably in the real world, despite the uncertainty. Now, one instance of what you said basically becomes a POMDP, right? Because now once you're given if we assume that our simulator is good enough, then it has a reasonable model of uncertainty of the real world, and the rest of our job becomes now reasoning, or one particular formal model of such reasoning becomes a partially observable Markov decision process, right? We don't need to debate here whether this is the best or worst model for robotics. We just say, if you ask me, I would say, yeah, one of the best, but let's just take one of them, right? So now we have a formal model, partially observable Markov decision process. Once we have that, then we know that in the worst case, it's bad. There's no way we're gonna solve that problem, right? But let's come back here, and like Fabio was saying that, but in practice, how about in practice? I mean, do we solve POMDPs in practice? We do, right? And under a few assumptions, we have to kick out some worst cases, right? I mean, we need some kind of, if we want to guarantee good performance, reliable performance for our robots in reality, we need to give some kind of packs that probabilistic bounds, which kicks out some of the worst cases, those kind of bad, and hopefully let me not hit that. For the rest of the things, we can have approximate solutions that are reasonably good, right? So this is roughly where we can get to, and also that we may have to have reasonable performance objective. I think that connects to what Dorsa was saying earlier. I think that we may not be able, even if I know that this is a POMDP, but that doesn't mean that I have to solve it as a POMDP. That does not mean that I have to use a standard generic general purpose POMDP algorithm to reason about the model to solve it, right? So I might just decided that yeah, for my particular task that yeah, like for example, food manipulation, right? If you think about Dorsa's example of food manipulation, how many of us actually be able to predict, like if I do something, I mean, stir something in my bowl, exactly how the finite element representation of that deformable thing actually would happen next? We don't, right? We just scoop it up, we stir it up, and this is basically a policy. We are not making predictions. We are kind of regress our policy or controllers against our experience and achieving desirable effects, I think. So I think in summary, I would say that a high-fidelity predictive model, a powerful model, efficient, computationally efficient model, all great. It is one of the tools that we want to use, not the only one. It's sometimes sufficient, but definitely not necessary.
And just to add on, yes, I agree with David, everything David said. And just to add on to that point, so I think, yeah, Fabio, you're talking about variability and uncertainty, and these variability and uncertainty theoretically can be captured by a simulator. I agree that they can theoretically be captured by a simulator, but it kind of like goes back to like the assets that Animesh was talking about. Like in practice, we don't have any of these assets, right? Like in practice, I have no idea what are the human suboptimalities are. Like cognitive scientists have no idea what are the human suboptimalities are. Like the reason we are suboptimal when it comes to playing chess is very different from how we are suboptimal when we are like driving a car or riding a bike. And we don't have even good models of that, like those complex types of decision making. So if we don't have good models of that, we don't really have access to those assets to put them in a simulator. I would argue that even for the simplest tasks, like pushing a block, we don't know what those variabilities are to actually like put it in the simulators. So sure, like theoretically, these variabilities, uncertainties, non-determinism, stochasticities, they can be captured in a simulator, but like, I don't know what those assets are. And so it seems like the bigger problem is figuring out what those assets are and then putting them into a simulator.
We are slowly approaching the end. I want to give Animesh another chance to address the points before, and then I'd like either Dorsa or David to make a closing argument for your side. And then after that, either Fabio or Animesh to make the closing argument for your side. Okay, so first, Animesh.
Thank you. I'll try to keep it brief. So I think to answer this question from David, I think we are not trying to argue that simulator will solve the optimization problem. I think one way to think about this is there are two aspects of the problem: specifying the problem and then optimizing to find the solution for the problem. I think simulation is a tool to specify the problem. I don't think simulation is the tool to find the solution for the problem. For that, we need algorithms, whether model-free, model-based, or however we are going to solve it. That's one. I think you gave a very good example of the fact that often we don't actually need predictive models. We have regressed to essentially closed loop policies where we are not thinking about the underlying models. We're just directly outputting solutions or policies. But often to arrive at that, you need sufficient amount of interaction and data. I think that is the part where the devil is in the details. Where is that data going to come from? Practically doing this sort of bowl stirring in the real world may not be possible. And I would try to close this, at least my argument was. So Dorsa gave a very good example, right? That often we would like to do a simulator of complex things. Feeding is one example, but we just don't have it. Right. And in that case, it's probably easier, perhaps even very tempting, to create a solution that is using with parametric approaches, things that I know of or about. This is where I would invoke, and this is not my personal opinion, this is a thought for food for thought, is Sutton's bitter lesson. It is often very tempting to create hand-tuned solutions, particularly in broad fields of AI. But often in the long run, we should be building structures to collect data and creating algorithms that learn like us, not necessarily learn what we have learned. I think I'll end my setup here.
Okay. Now, David or Dorsa, who wants to go for the finale?
David, do you want to go for it?
You want me to go first? Oh, sure. Yeah. So I think the way I look at Sim2Real is that it consists of 3 parts. And the first one is prediction, accuracy, and efficiency. That's the sim part. That better simulator improves the final outcome in general, on the average, right? And second part is about reasoning about the simulation models and derive the control and then policies. I think these 2 points mostly overlap with Animesh already said. But then the last part is really about transfer from the simulation domain to the real world. And there is a gap over there. We have to assume that there is a gap over there. And if it were not there, then there will be no workshop over here. And this gap, oftentimes, we don't have, for any given task, we have only limited understanding of that. And that's basically the variability and uncertainty. And what do we need? And I think that of all these 3 aspects, I think in this last aspect, we have the least amount of theoretical understanding of how to characterize this gap and what information we need and what structure we need to put in here in order to systematically go from a source domain, a solution computed in the source domain, and transfer it into the real world and do that effectively and robustly and achieve good overall robot performance. I think this is the most important question for Sim2Real.
Thank you. And then Fabio or Animesh, who wants to go?
Fabio, why don't you take it over? Yeah.
Yeah, sounds good. So I wanted to finish with a summary of things that both teams agree, and then things that we don't agree. The first thing we agree is that we don't need super accurate simulators for everything. What we do need is, good enough simulators for the task we have in hand. We agree that the Sim2Real problem is not just about simulating reality, but it is about capturing or deploying an algorithm in simulation and expecting that algorithm will have a similar kind of performance in real. And I think that's a very important point, that it's Sim2Real, the Sim2Real problem is always contextual. It's contextual on a task, a policy you want to learn, an algorithm you want to try, and then verifying that the reality behaves the way you expect on that algorithm, on that method. So these are critical points that we agree. What we don't agree is that, in my opinion, that given the tools we have available to us, which are parallel simulators, fast, some of them are differentiable, we can recover the reality in expectation. And if we can recover the reality in expectation for most practical problems we have in robotics, this is the way you should at least start reasoning about your problem. Even, let's say the problem is too complicated, you cannot have your PondDP to solve in Sim. Well, it won't solve in reality, it won't solve in Sim. So for me, that's a perfect, valid Sim2Real translation. It's not solving in one place, it's not solving the other place. I'm happy with that. The Sim2Real problem is under control. That's the other problem, is the decision-making problem, but the behaviors are matching one side and the other. And if we have behaviors that match in simulation and reality, I'm confident that we have practically solved the problem. And let's hope that people keep on doing research on this area, because next year, in the next workshop on this, we can remove the word practically from the sentence, and it will be an even more interesting debate for us.
Yes, please give a hand to our debaters. Okay, now to close off this debate, I'm going to open a Zoom poll on who you think has won this argument. And please keep in mind, Zoom attendees, this is about the argument, not about if you yourself think Sim2Real or not is solved. And while this is happening in the background, I also want to get the audience in the room. Please clap if you think that Dorsa and David's side made a better argument. Okay. And please clap if you think Animesh and Fabio made a better argument. Okay, very respectable. Okay, so from the online poll and kind of from the audience as well, I think Dorsa and David came out at the top here. So congratulations.
well, we should thank the organizers. We just had the easier side of the argument.
Also, thank you, Animesh and Fabio, for arguing this very difficult point and for entertaining us with this great debate. Thank you so much.
Thank you all.
Thank you all. It was great fun.
And Animesh, at some point, you must have thought that you wanted to agree with us, right?
Well, as with these debates, the answer is always in the continuum.
It was great to see everyone. Thanks a lot. That was fun.
Thanks a lot. Thanks a lot for making time.
Thank you. It's great to see all of you.